All right, Master of Science students, let us proceed. Uh, there are some terminologies which I'll mention, and once again I'll mention in a past time because okay, I think I should mention this for us as teaching staff. Usually have something called a gentleman agreement that. You don't do it. You don't venture into your colleagues' area of domain. Think just let them be the boss in that area. For example, if it is something, for example, which may be dealing with organic chemistry, the one teaching physical chemistry may just say this this terminology or this concept you are going to be taught in organic chemistry, or maybe if it is inorganic or analytical chemistry, as opposed to trying to tackle it at that level. So I'll just mention a few things, but once again, this these terms you are going to know about them in the physical chemistry course. The reason why I'm saying this is the fact that they'll be in one way or another. So you're going to hear what like state functions and the rest. Yeah. So this the system surrounding the universe, which is uh, the whole system, which includes the surrounding plus the system. In this case, the system is the one where the chemical reaction is taking place. Yeah. So that's the word that you're going to use, the system, and then there will be the surrounding. In this case, the surrounding can say the heat is either going into the surrounding or uh, coming out of the surrounding, and then the combined system plus the surrounding gives the universe. Yeah? I hope you'll be able to distinguish between the universe in this case, and the and, and the universe that you know that is composed of the galaxies and the planets and everything else. Yeah, I hope that's not the universe you're talking about. This one you're talking about just a restricted place. The the chemical setup that you're talking about is called the system, and then the surrounding, and then the rest is called the universe. It's an outrageous term calling all that from the universe, and you know the universe is quite a vast area, but okay, that's what you will be talking about. But in physical chemistry, uh, um, the rules should apply to the whole universe. But once again, it's a bit debatable because we do not know a lot of things. We can predict something mathematically, but unless you can verify it with what with the experimental evidence, it will just be what it will just be mathematical equation. But once again, I do not want to venture that one. But so far we've had the most successful equation, the general theory of relativity, having explained what is happening in the universe. The one which was developed by Albert Einstein in 1915. Yeah, yeah, yeah. About talking about the black holes and everything, and the movement of I mean that the empty space. Just be saying empty space, but it's actually that which you're talking about. The empty space is actually can be warped by gravity. It can be turned around and the rest. So uh, that's the real universe that we'll be talking about, and that which you're talking about, like the light, is actually traveling. If we're talking about the space, yeah. So if the space is curved, then the light that is going to come to you is going to be curved. I mean, it's going to be bent, yeah, as opposed to moving in a straight line, yeah. So when you're talking about light moving in a straight line, it means that there is no big object which is bending the gravity before that light comes to you. But that's another thing. So that is the normal universe that you're talking about. But in this case, you're talking about like a localized universe. which is composed of the system which you are analyzing and the surrounding. So let me mention a few things, but once again, you learn about them in physical chemistry. So you'll be hearing words like state functions. So these are the parameters that determine the current state of a chemical system. And though probably you may get more, but for now we'll just need to know about these few state functions, just about six. Yeah. Uh, there's the pressure, volume. Uh, this is the absolute temperature in Kelvin. That's the enthalpy. That's the entropy, and then there is the free energy. Yeah, or the ability to do work. Okay. And then the other thing which I've, which I also put like in the previous video, but I think I'd rather mention is that the change in the state function is given by the delta sign. So if you're going to have a delta H, it means that there is a change in the enthalpy. Yeah. So which is given by the final state minus the initial state. Please note this: the delta means the final state minus the initial state. But once again, those are things which you get into the physical chemistry. Now, something worth mentioning are these units because in the kinetics and thermodynamics, you may have problems and or equations to solve, and knowing about the unit really matters. So the free energy, which is called the free Gibbs free energy, is normally represented by kilocalories per mole. But as you know, uh, calories can be converted to the SI unit, which is the joules by multiplying by 4.184. Yeah. So if if you require the answer to be in SI unit, like in joules, and the things, and the parameters or the state functions are given in calories, you can multiply by 4.184 to convert calories. Calories is bigger than the joules by 4.184. Then there's the delta D, which is the standard free energy. So please note there is the zero sign. So in this case, we'll be talking about standard temperature, which is 298, which is the room temperature, and then the pressure, yeah, atmospheric pressure, standard pressure. So there is the standard free energy. You're going to hear that word G is the absolute, but this is the standard free energy. Enthalpy in kilojoules per mole. Temperature, if you're given in calories or not calories, but Fahrenheit and Celsius, yeah, then you have to convert to Kelvin. S is the entropy. Please note the so there is the kilocalories per mole, which is the same as the other one, but then there is per Kelvin. It means that if you're going to multiply S by T, then you're going to get the total energy. Yeah? I mean energy of that component. So that means that Kelvin multiplied by the change in the entropy is going to give the energy in kilojoules per mole. Yeah. So keep note of those changes. There is the gas constant 0. Or the once again, let me just avoid those the 8 point whatever 0.082 or those kind of things. Uh, Let me leave about those things, uh, but something which may be worth mentioning as well is about the you're going to hear CP, which is the concentration of the products, and then the CR, the concentration of the reactants. And then a very important terminology, the equilibrium constant K, and then there is a subscript of equilibrium. You're going to hear those that terminology, whereby the equilibrium constant gives the the the, the product of the concentrations of the product divided by the product of the concentrations of the reactants. Yeah. So that if the concentration of the product is greater than the numerator is greater than the numerator, then the equilibrium constant will be at least greater than 1, yeah? So, but you're going to see that one later. So there is the progress of a reaction. This is not the kind of the progress, of the reaction coordinate diagram of which you get, but I think it's worth mentioning that 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 uh, the products and the starting material are going to have a certain energy, but if you're going to let them equilibrate, you're going to have a certain concentration of probably some of the starting material and some of the products, yeah? So they will be in equilibrium with one another. It means that some bonds are forming, some other bonds are breaking, yeah? So it's not an absolute pure products or pure reactants, yeah? An equilibrium. It means that some some products and some reactants are forming. Can you mention one of the? I just want to mention one of the things which you've dealt with as an equilibrium. For example, the formation of an ester from a carboxylic acid and an alcohol. So you're going to be forming an ester plus water. So this is an equilibrium, which means that the ester plus the water can react to form the carboxylic acid plus the alcohol, and in this other case you can have the carboxylic acid plus the alcohol. They can react to form the ester plus the product. So what normally happens to drive the equilibrium forward will be uh, uh, in this case will be to do what? To remove one of the products. In this case, if you're going to be probably doing a reflux, in this case the water is going to be boiling off as steam. So in this case, that's a way of pushing the equilibrium to the products, yeah, to increase the concentration of the products. But once again, this is an important terminology: K equilibrium constant. Okay. So coming back to this equation of the free energy being equal to the enthalpy minus the temperature multiplied by the change in the entropy, which in this case, though in one case you can call it a degree of disorder, but I think that's just a vague term. But you'll be able to get the exact definition of the entropy. But what I'm going to see is something like just in mention. Is it like a degree of disorder? What you're going to see is that solids are more ordered than liquids, and liquids are more ordered than liquids are more ordered than gases. So you're going to say gases have got more entropy than liquids. Liquids have got more entropy than the solids. But in general, what you're going to see is that if you're going to have many reactants, and that's what I'm saying, you may not be talking about this as the degree of the disorder, because entropy is a bit complicated term. If you're going to have many reactants coming together to form a single product, then that's going to bring to this other definition of the entropy, which is the degrees of the freedom. It means the resultant products have got less degrees in which along the X, Y, and Z in which it can move, as opposed to if there were individual components, they can move in different directions, as opposed to one unified cannot move in one direction before disrupting other parts of the or of the same molecule. So if you're going to have many components or many starting materials coming to form one single product, then you're going to say the entropy is going to decrease. But the converse is also true, that if you're going to have a single starting material and then it's going to give many products, then there will be an increase in the degrees of freedom, and therefore the entropy is going to increase. So once again, as I mentioned, it's a bit of a tricky term. In one case, it's a degree of disorder, and in this other case, it is the degrees of freedom. Yeah. So entropy has got different meanings. So I've now put here different scenarios in this last one here as to uh, uh, what's going to happen. What you want is to know whether the reaction will be spontaneous or not. Do you remember what I said in the last video? For reaction to be spontaneous, delta G has to be negative. Delta G has to be negative. If a reaction is not spontaneous, then delta G is positive. So this is giving scenarios in which delta G can be negative or it can be positive. So and once again you can put this, but I think it will be good if you're going to get time and just give figures and say, hey, I want my enthalpy to be probably 200 kilojoules, and then I want to see this reaction taking place at 298 Kelvin, and then maybe changing the entropy will be probably be maybe 2 kilojoules per mole per Kelvin, yeah. Or maybe I want to say the delta S is now negative, yeah. Uh, so if you're going to put these kind of things, you're going to get this kind of this scenario. So, but in general, if the delta H is less than 0 and then the delta S is greater than 0, it means that if this thing is greater than 0, then this terminology will always be negative. Yeah. If the change is positive, then the T delta S will always be negative. And if this is negative, then the delta G will always be positive. No, will always be negative. Yeah. Negative here, it means that if this is negative and this terminology is negative, then the final answer will be negative. And conversely, yeah, we want to look at the last scenario in which if the delta H is greater than 0, it means that what? Do you remember what I said? If the delta H is less than 0, then the reaction is exothermic, as opposed to if the delta H is greater than 0, then the reaction is endothermic. So you can be able to put here this A endothermic, and this is exothermic. Okay? Can you see that? This is delta H being less than 0, and this is the delta H being greater than 0. So if the delta H is greater than 0, yeah, so it means that this terminology will be positive. And then if delta S is also greater than 0, no, it's also less than 0, sorry, it's also less than 0, then this terminal T delta S will always be positive. So whatever happens, delta G will always be positive. So in that case, the reaction is not going to be spontaneous. As opposed to these two cases are giving the scenario in between as to if you're going to have delta H being less than 0, delta H being positive more than 0, delta S being less than 0, delta S being more than 0, and then it's telling you because what you want is for you to get a negative term. It means that that if this is positive, then this one has to be negative and uh, larger than this one. So in that case, so for example, if you're going to have 20 minus 20, then in that case you're going to get a 0. But if you're going to have 20 minus maybe 25 or whatever, then this terminology is larger and but negative than this one by 5 kilocalories, and therefore uh, in that case you're going to get a spontaneous reaction. So this is just giving you the various scenarios, so that in this case this is telling you at low temperature the reaction will be spontaneous. In this case at high temperature the reaction will be spontaneous. Yeah? So these are the various scenarios that you're going to encounter. So after this now, we'll now start looking at the reaction coordinate diagram and then the final aspects of the thermodynamics, and then we'll go to the kinetics later. And then from the kinetics, we'll now look at some aspect of the equilibrium constant and a few other things. Yeah. So I think I'm just going to stop there, and then we'll proceed on with the with the course shortly.